Okay, now this is the big major result. There's not many things we actually argue or prove, and those that we do are really easy to do. Most of the homework, in fact, is just the computations, and it's not actually this theory. But this next result's really critical for what we're going to do in the next section. And it certainly deserves an explanation why it's true. So if you remember the matrix I just gave you, it had eigenspaces whose basis was the vector 0.4, 0.6, and there's another eigenspace, E sub 1/2, whose basis for that space was 0.1 and negative 0.1. But if you look at those two vectors, they were linearly independent. If you took the basis for the first space, took the basis for the second space, those vectors by themselves were linearly independent separately. When you put them together, the result is actually still linearly independent. Now, if you look at another vector, another matrix, this one, it had two eigenspaces, one for the eigenvalue of 1 and the other for the eigenvalue of 3. In the first eigenspace, E sub 1, it had a basis of two vectors. Those two vectors by themselves are linearly independent. The second eigenspace, E sub 3, had its own basis. It had only one vector in it. That one vector by itself is linearly independent. Now, if you take these three vectors and put them together, it just so happens that they are linearly independent automatically. And the reason is because of the theorem I'm about to prove to you. Now, some of you might say, well, yeah, that seems like it should always be true. You take a subspace here, you take a subspace here, all these vectors are linearly independent, all these vectors here are linearly independent. When you put them together, they should be linearly independent. No, no, not true at all. Not true at all. And in fact, it's possible to get a bunch of spaces in an overall space. Take a bunch of subspaces where there's a couple vectors here that are independent, a couple vectors here that are independent, a couple vectors here that are independent, and all the spaces have nothing in common. They only have the 0 vector in common. And yet when you take these separate vectors that are independent and put it together, it's still dependent. It's not linearly independent. So then this is something that's important and it's special to eigenvectors and eigenvalues. It's a special fact about eigenvalues and eigenvectors. Also because for every eigenvalue, there's a finite number of eigenspaces. You can't do this too many times. You can't add on too many vectors. So that's, again, a reason why it works. We definitely need a proof. So here's the theorem. If anyone wants to, after they say this, if you want to skip to the end, you want to just skip the end and not watch the rest of it, you don't have to. This is just a proof. It's 4 pages. Not because it's hard, it's just the notation's kind of long. So I went on a board, it's not that bad. It's only like, like a half a board. That's it. It's all half a board. But in here, I have to carry equations over constantly in order to make sure you understand what the hell I'm doing. Understand you don't get lost with the notation. So it's not a difficult proof. It's just there's a lot of stuff. A lot of notation to write down. Okay, so suppose you have a square matrix. Say B sub I is a set of linearly independent eigenvectors that correspond to an eigenvalue. It's not a basis for the eigenspace. It doesn't have to be. I just want a bunch of linearly independent eigenvectors corresponding to a certain eigenvalue. But when I do this, though, all the eigenvalues I'm going to talk about are all distinct. So for each set, B sub 1, B sub 2, B sub 3, B sub 1, B sub 2, they come from different eigenspaces. B sub 2, B sub 3, they come from different eigenspaces because they come from different eigenvalues. It winds up being then, if you take all these different collection of eigenvectors and pull them all together into one big set, it is always linearly independent. So let's see why. All right, here we go. You know, it's the proof. So then let's say that you have a bunch of sets. So the first set I'll call B sub 1, the next set B sub 2, the next set B sub 3, all up to the very last set, which is B sub k. They are a set of eigenvectors. So then I need to write them some way. So for B sub I, the vectors in there will be x sub I1, x sub I2, x sub I3, up to x sub I. I don't know how many there are. I'll call it n sub I. So it's x sub I, n sub I. So there's n sub I vectors in the space B sub I. Don't worry, we won't see that again. It's just notation, unfortunately. I had to write it down. So it's a finite number of vectors. Okay. Now I'll do that for every eigenvalue. That means for every set of vectors I have. Let's form a linear combination, oh God, of all of these vectors. Here they go. Here is a linear combination of all those vectors. It's going to equal the zero vector. I got to prove to you that every single one of those scalars is zero. Well, there's a couple of tricks we can use to make our life a little easier. First off, these are all eigenspaces. B sub 1, B sub 2, they all come from different eigenspaces. So then for each set of parentheses, call that a vector. So the first set of parentheses, well, that sum is the vector I sub 1, X sub 1. The next one, the next set of parentheses, they all come from B2. That will then be the vector X2, and so on. It winds up being, though, that X sub 1 is in the eigenspace, is in the first eigenspace. X sub 2 is in the second eigenspace. X sub 3 is in the third eigenspace, and so on, because each eigenspace is a subspace and they are closed under linear combinations. So then this here is a linear combination of vectors that are in the first eigenspace. So then because it's a subspace, this would then be in that very first eigenspace that goes with the very first eigenvalue. This last guy here, these are all vectors in the last eigenspace. So therefore, since it's a subspace, this thing has to be, this corresponding vector would have to be in the eigenspace for that very last eigenvalue. There you go. So that's one way to make it easier. We don't have to look at all those subscripts for now. We just have now a sum of vectors, x1 through xk. x1 is in the first eigenspace, x2 is in the next eigenspace, and so on. All right, so here's the equation all over again. Thing is, though, that when I add those vectors up, I don't know which of them are zero or not. So then let's argue. There's only two possibilities. For each of these vectors, either it's a zero vector or it's not. If it's a zero vector, it's just a zero vector. If it's not a zero vector, then it has to be an eigenvalue. It has to be an eigenvector for the corresponding eigenspace, because the eigenspace is the set of all eigenvectors, and anything that's not zero in it is an eigenvector for that eigenvalue. So then in each of these things, either it's the zero vector or it's a eigenvector for the corresponding eigenvalue, lambda sub I. Okay, but at the beginning, I called the sets of vectors B sub 1, B sub 2, B sub 3. The names are arbitrary. They're arbitrary. I just wrote them down. I could call this set over here B sub 1, and then call that guy over there B sub 2, and so on. So then I can relabel them. I want to relabel them from the very beginning of the proof so that all the non-zero vectors occur first in the sum, and all the zero vectors come last. We are allowed to do that because we're just changing names of things. If I call you, if your name's Bob, and your friends call you Bobo, calling you Bob or Bobo doesn't matter. I'm still talking about you, right? Okay. So here, I'm just going to relabel those sets in the very beginning so that in this particular sum that you see, x1, x2 up to xk, that the non-zero vectors, if there are any, are right at the very beginning. Let's just say there's r of them. So x sub 1, x sub 2, x sub 3, up to x sub r. Those are the non-zero vectors. Everything else, zero. That means that in that equation, only the first r vectors matter because the rest are zero anyway. That gives you that equation. I now have a linear combination of vectors x1, x2, x3, up so on, so that these vectors are all eigenvectors for certain eigenvalues. Relabeling them, the x sub 1 has the eigenvalue lambda sub 1, x sub 2 has the eigenvalue lambda sub 2, and so on, because I relabeled everything to line up correctly. Now, that means then that since this linear combination adds up to 0, that means that, and there's a non-trivial one, these vectors are dependent. They are linearly independent. They're linearly dependent. From a theorem I gave you before, that means one vector is a linear combination of those before it. That has to happen. One vector is a linear combination of the ones before it. So, reading from left to right, x sub 1, x sub 2, x sub 3, x sub 4, x sub 5, and so on, find the very first vector in that order. so that the vector is a linear combination of what came before it. We will say that vector is x sub m. So x sub m is a linear combination of the vectors that came before it, from x sub 1 to x sub n minus 1. The scalars using that linear combination, I don't know. I only know it's a linear combination. But that means then that the vectors x sub 1, x sub 2, up to x sub n minus 1, they have to be linearly independent, because if they were dependent, then one of those vectors would be a linear combination of those before it. And x sub m is the first such one. So we now know that x sub n is a linear combination that came before it, and x sub 1 through x sub n minus 1 is linearly independent. Also, we can say one more thing, and that is, since x sub 1 is non-zero, then m is at least 2. So there is at least one vector here in this list that is linearly independent. Cool. Now we have that. We have the framework. Okay. Now that I have this framework, I underline above the assumption. I assumed that some of them are not zero. I'm going to show you that can't be true. All these vectors, x sub 1, x sub 2, up to x sub k, whatever they are, they're all the zero vector. Once we get that, the proof is incredibly easy. So I'm going to show you that the assumption that at least one of them is non-zero can't be true by using what you see in number 3. Okay. So here's number 3 again. X sub m is a linear combination of the vectors that came before it, and the vectors that came before x sub 1 are linearly independent, and m is at least 2. Take that particular equation. I want you to multiply the equation 3 on the left by lambda sub m, and also on the left by a. That will let you form 2 equations. So the first equation 4, just take equation 3 and multiply the whole thing by lambda sub m. I just recollect the terms so you can see it. Then multiply on the left by a. But notice, remember, if a vector is a linear combination of eigenvectors, it's easy to do so. You just multiply the matrix through, and you replace the matrix multiplication of a times an eigenvector with the eigenvalue times the eigenvector. So that gives you this. Just multiplying that equation 3 all the way through by a. Notice that both equations have the same left-hand side. So subtract them. So we subtract them and get that. Notice that means that we have a linear combination of x sub 1 through x sub n minus 1. We know, though, from remember, that those vectors are linearly independent. So since they're linearly independent, every single one of those scalars that you see multiplied to the vectors is 0. So then this thing here is 0, this thing here is 0, and so on. But if you look at each of those constants, it's a product of 2 numbers. One of those factors is a difference in eigenvalues. In this case, it's always lambda sub m minus lambda sub something, but the something is less than m. If you remember, all the eigenvalues at the beginning were all different. So those differences of eigenvalues are not 0. Well, if each of these coefficients has to equal 0, and the difference in the eigenvalues are always non-zero, that means C1, C2, C3 up to Cn minus 1, those are all 0. But if they're all 0, go back to equation 3, you see then x sub m is the 0 vector. And that's impossible. Remember, x sub m was among the first R vectors. X sub m is not 0. I just showed you that it had to be 0. So that means that my assumption that x sub 1, x sub 2, x sub 3, up to x sub k, x sub r was all non-zero. So that can't be true. They all have to be 0. They're all the 0 vector. So we now know that in this linear combination that you see, x sub 1, x sub 2, all those vectors, x sub 1, x sub 2, up to x sub k, those are all the 0 vector. So each of these little all these little sublinear combinations, they all equal the 0 vector. But they're equal to 0 vector. That means that all the scalars here have to be 0, because in each grouping, I assume that those vectors were linearly independent because they came from b sub 1, b sub 2, b sub 3. So these vectors here, these guys here, all came from b sub 1 and x sub 1, 1, x sub 1, 2, x sub 1, 3, and so on. Those were linearly independent. So all those scalars, this guy here, and this guy here, and so on. Those are all 0. These guys all come from B sub 2. But this vector up to that vector, those were all linearly independent because that's how I formed the set of vectors. So since this set of vectors equals x2 and x2 is a 0 vector, that means that all the scalars, this guy here, they're all 0. That then shows you that if you just repeat this argument over and over again for each of the parentheses, that every single scalar you see here has to be 0. So that says then that if you have B sub 1, B sub 2, B sub 3, so on, and these are all linearly independent vectors coming from different eigenspaces, so therefore different eigenvalues, if you take that set of vectors and put them all together, it is always linearly independent. And that's the proof we have to get through. So the last step would then be is if we can take a bunch of sets that are linearly independent and put them together to get a much larger set of linearly independent vectors, is it enough to be a basis? That's what the next section of the book's about, is talking about that very question. As in the end, it leads to an amazing, amazing computational technique. Like truly, one of the reasons that we even have linear algebra is because of this result. Truly cool result. And I believe that's enough for that video.